Good afternoon, everyone. I am Atanu Chatterjee. I have come from India. I am a student, a first year master's student, and I am working in the area of network science and its integration with the civil engineering, the urban transportation networks. But I have an interest in the field of complexity science. I did my bachelor's in mechanical engineering, and I find the idea of thermodynamics very fascinating. And during this seminar, we will see how self-organization is a product of thermodynamics, mechanics, and how we can model it using these two frameworks of physics. So the title of my seminar is Physical Foundations of Self-Organizing Systems. So I did my course this last semester I did a course in probability, and towards the end of this course I realized that science is quite boring. So why I found that, this is the simple, because we have these two laws which I learned towards the end of my course. One is the strong law of large numbers. What is strong law of large numbers? Strong law of large numbers is that I have a dice. The mean of my throw would be 3.5. It is just calculating that the probability of getting 1 is 1 by 6. So 1 by 6 times 1 plus 2 times 1 by 6, and you sum the entire thing and you get a 3.5 for a single dice. Now if I have a collection of dice, suppose maybe 2000 trials if I make, then the number, it gradually converges to 3.5. So that is basically stating the thing that you have a single particle, and you have a group of particles, and the interaction of a group of particles is equivalent to the interaction that a single particle is being forced upon. The second law that is often considered the cornerstone of probability, that is the central limit theorem. According to the central limit theorem, we have n number of random variables. We add those random variables and we gradually emerge with a normal distribution. We have a couple of people here, and if we assign the height distribution as a random variable and then we fuse all those things together, then maybe we will get an average height of something about 5 feet 6 or 7 inches. And towards the one extent there will be shorter people, and towards the another extent there will be tallest people in this room. So these two things made me realize that science is quite boring, because after all everything gets freezes on to the mean, or defining a collective phenomena is equal to defining a single phenomena. That's all what we have been doing. This is a simple cartoon where even a dog is giving in financial ideas how to invest in a herd of cows, because his risk will be minimized if he goes towards, if he invests upon a bunch of cows. Because it's a math. You can't deny this fact. So these are two fundamental laws of probability, mathematics, that finally made me realize that mathematics is boring and science is boring. That's what I was saying, that collection of entities is equivalent to single entity. That's nothing but reductionism. We are analyzing a group phenomena from a single phenomena. This is a Newtonian paradigm of physics, where we have solved this kind of problems, where there is a car which is moving at a velocity of 100 miles an hour, that is equivalent to a single particle that is moving at 100 miles per hour. So what is the difference? The difference comes when we have an aggregate. When there are n number of particles in a confined space, what happens? There is an interaction. This is a classical thermodynamic example, statistical thermodynamics example, where we have collection of particles, they are interacting. Suddenly what happens? We start to feel the temperature that starts appearing outside the walls of this container. This is because of constant dissipation. This is because of constant interaction. So finally I realized that science is not so boring, because these two laws, the central limit theorem and the strong law of large numbers, they fail to hold in reality. Why do they fail? Because in reality, systems are correlated. In ideal mathematical sense, we define the random variables or we define the numbers, they are not correlated. They are completely independent from each other. But in nature, in reality, everything is correlated. My action will define someone else's action, and it will in turn define an entire group. So now we come up with this term, the action. We will see what this term action has a significance. So this is a picture which says God doesn't play dice with the world. He was proved wrong by quantum mechanics, but I'll say that in this regard he is quite obvious and he is quite correct, because God really doesn't play dice, because central limit theorem is not what we need to understand nature. We have something greater than that. So now we define self-organization as a spontaneous appearance of global order through local interactions. I have highlighted the word spontaneous and interactions. Spontaneous gives us a dimension of thermodynamics, and interactions gives us a classical mechanics or a mechanistic dimension. That means we have a emerging order when there is an interaction at a lower level. So this you can see the spontaneity, the interactions and the global order. We will see how these three things are making a interplay with each other that will help us to analyze the self-organizing, and that will help us to define the laws, the foundational principles for self-organization. Spontaneous and interactions. Now spontaneous, we need to define what is spontaneous. Spontaneous is something which is naturally driven, which does not depend upon some external parameter to influence its occurrence. It will occur in itself. Interactions as we know, it is just the interaction means you can say that it is just a transfer of something from one thing to another thing, which are constantly correlated maybe. So you can see the entire thing, it can be explained as a cycle that global order emerges when spontaneity and interactions occur hand by hand in a parallel way. Now we come to the domain of self-organization, where self-organization is a distributive phenomenon. It is not a property of the system, but it is a property of the individual elements. How these individual elements, how this self-organization is distributed among the particles which are constituting the entire system. Now spontaneity is a natural process. We define natural process. Natural process is something which is naturally occurring, which does not need any influence, any external influence. And interaction is ultimately the correlated action. We will define what actually action is. A naturally driven process is a process which aims to equalize certain gradients. These gradients could be anything from concentration, energy, matter. The temperature is a measure that energy is flowing from the higher end to the lower end. The diffusion is a principle where we can see that the concentration is being equalized from the higher areas to the lower areas. So natural processes are those processes which thrive to equalize these gradients in nature. So natural processes will tend to make the systems go towards a state where there is no difference. The things are equilibrated. So self-organization does not occur as a result of any central directing authority. There is no single person who is directing that this is the rules according to which the every element will be behaving and entire system self-organizes. It is not the case. We see a picture of the swarming of the birds. The swarming of the birds is a classical example where you can see the birds have emerged a shape of a V structure. A V shape enables them to fly more efficiently for longer distances because it reduces the drag, it gives them lift towards the neighbors, it gives them a better flight, it helps them reduce something about 12 to 20% of their energy. Now we come to define what is action. Action is a classical term which has come from the classical definition of mechanics which was formulated by Lagrange. Here L represents the difference between the kinetic energy and the potential energy. So this L dt, the integral of L dt, if I observe a system that is moving from one point to the another point, then its kinetic energy and the potential energy is always changing. The difference between their change, the difference between kinetic and the potential energy, which is integrated over time, this is actually the action. And this enables us to reach a concept of principle of least action. The principle of least action, we know that if light travels from one place to another place, it tends to take the shortest trajectory. The time for which the motion would be very less. This is a logical and a very reasonable attempt. Even we, when going from our home to our workplace, we take the shortest route. Irrespective, there are n number of routes available. The principle of least action is, to some extent, it is deterministic, but it is quite logical. We have a very strong principle, that is the Noether's theorem. Noether's theorem in modern physics, according to which if any system has a continuous property, like the symmetrical properties, like there would be a property of mass, there is a property of translation along the axis, there is property of rotation about the axis, then there will be certain corresponding quantities that will be conserved in time, like linear momentum, the energy, the angular momentum. They are conserved with respect to time. So if any process has to occur, the symmetry should break. The symmetry of the system should be less than or equal to that medium in which the process is being taken place. So we have a simple pictorial example, like we have an object which has something 11 photons, which is made up of 11 quanta, and the another object which is made up of 7 quanta, and some externally influenced 1 quanta comes up and they all combine and their symmetry class increases to 19. So if any process has to occur, the symmetry has to break. This is ultimately imagining like two cells are there and they are coming together and they are combining and they become a big cell due to interactions. So this is the earlier example. What we see is that one is the dotted path. This is naturally the shortest path because it is along a straight line, and there are n number of paths available. So what we do is that we define a path like the actual path, which could be anything like the green or the blue or the red, and it is something equal to the shortest path, that is the dotted path, plus some little displacement which I quantify with the epsilon of t. So we try to make a formulation of the principle of least action for a multi-agent system. The principle of least action has been studied for single systems, where we know the initial point, we know the final point. It is completely deterministic mechanics. But when we have a collection of particles, when we have n number of particles in a confined space, we know their initial states, but we don't know what are their final states. We want to compute how that system will evolve with time. So we need some kind of formulation where I have denoted a pair of particles as ij, pair of particles, and I have defined the action for a pair. Pictorially we can imagine it like this. We have so many particles and they have different trajectories across this grid, and they want to go from one place to another place. So if possible, someone comes from that corner of that room and someone comes from that corner of that room and they will collide at the center. So there is possible some collision may occur, some dissipation will occur, some energy will be transmitted from the surrounding walls to the environment. So this is possible. But what will happen for the system as a whole? The system will become excited. The system will become very chaotic. But that is not a natural tendency. We don't see systems like they are quite stable in nature. They are quite stable. We don't see people like evaporating spontaneously. They have a specific framework. They remain as a stable entity. They are in their lowest energy state, according to the principle of least action. So the difficulty we face when we model a system using the principle of least action for a multi-agent system, the difficulty is that the differential equations that we arrive at, there are n number of differential equations and ultimately we end up getting no solution. So we need techniques. We need techniques how to solve the differential equations when we have a collection of entities which is not deterministic. So we need mathematical techniques which could be optimization, which could be game theory. Game theory is again a part of optimization, which could be computational techniques, cellular automata, which could be multi-agent simulation techniques. So these are ultimately the techniques which are using for understanding self-organization also. Now, game theory is of specific interest because game theory is a very logical explanation, because every entity in nature is somehow it is competing against the another. There is always a competition. There is always a competition between entities. There is a competition between cities, competition between countries, competition between two nations for war, for resources, for wealth, competition between two individuals. So there is always any kind of competition occurring. So every element tries to achieve a state where it will be stable along the time scale. So gradually it will give rise to competitions, but in a way it is a good method to understand the evolution of a system over time, because a system is made up of entities. Every entity wants to reach a ground state, a stable state, but conflicts, internal interactions will cause the system to get excited. But systems in nature, we don't find they are excited. Systems tend to lower their energy scale towards a ground state. So ultimately there is something happening inside the system that is preventing the system from taking a high energy state. So that thing, maybe that could be some kind of equilibrium, some kind of attractor which attracts the system to a state which is the stable state for the system. So we see a simple example how the growth of the system due to energy dispersal from one node to the another node, it is giving the graph of this normal distribution curve, it is becoming shorter and shorter because of the energy dispersal. As soon as the choices, earlier we had n number of choices because there were large number of states possible, because as the y-axis grows up, the number of microstates increases. As the y-axis comes down, the number of microstates and the possibility for dispersal of energy, it reduces. Finally, it goes towards a stable curve. Anybody has any questions, or if anybody wants to ask anything?
Yeah. Can you give some idea what you mean with game theory? What do you mean with that?
Game theory. Game theory is a concept, a mathematical optimization technique where we have the players, we have the strategies. The player employs the strategies in order to maximize certain quantity.
Okay.
The parameter that he maximizes, that is essentially called the payoff. So a game theory is a mathematical modeling technique through which we try to approach a state where the game will reach an equilibrium phase, so that the payoff for the entire system of the players will be at an optimum level. So that is basically the game theory. That was developed by von Neumann, and gradually it was the concept of equilibrium in game theory came up with John Nash, which we know as the Nash equilibrium. So that is game theory.
It's also the prisoner's dilemma.
Yeah, prisoner's dilemma. Yeah. So any further questions? So this is what I was talking about, the Nash equilibrium. The Nash equilibrium is an attractor. It is an attractor for a system. What is Nash equilibrium? The Nash equilibrium is that it is a set of strategy profiles for the players at which if certain player he knows that the opposition he will change his strategy, and if he tries to alter his strategy, then there will be no common good for the entire system. The system has reached a certain state that if you alter your strategy to maximize your personal payoff, it won't help you. That is a game theory. So what we see is that game theory, the Nash equilibrium, it is a kind of attractor for a game. Maybe the Nash equilibrium, like an attractor for a game, an n-person non-cooperative game, may be an attractor in a nature. Maybe the particles which are interacting constantly, they reach a certain equilibrium phase where there is no chance for further organization or further reducing their energy levels. And a deterministic dynamic system will automatically evolve towards a state of equilibrium and attractor. This is the idea that Ashby gave of self-organization. So self-organization are some attractors in spatial space, the phase space, where the systems, when they enter that state, they can't get out. That is a state where the system has the lowest maximum organization. That is the state where the system has its lowest energy capacity, or it's the most stable state, you can say. So we can find analogies. The interesting thing is that we can find analogies from different areas. Now we come to what is system. We have been talking about system, but what is system? System is something I define as a summation of action and organization. Action is something disorder. Organization is something order. Action is an output, or you may say a byproduct of interactions. Organization is something quite abstract to define. So a system has a tendency to reduce its action, that we know already. But how it reduces? It reduces by emitting quanta to the surrounding. If it has a high energy state, it will automatically, by common sense, we can say that it will reduce its energy by transmitting some energy to the surrounding medium. Vice versa? Yeah.
Are you talking about an isolated system or a system that still has...
No.
Open system.
Open system. Because isolated system doesn't come into this domain of complexity science, first of all. Because isolated system, when we talk about isolated system, we talk about thermodynamics of isolated systems, then that system will, with time, that system will completely destroy itself, according to the second law of thermodynamics. But what we are talking about are the open systems. We all are open system. We are constantly incorporating information. We are constantly incorporating energy through discussions. We try to talk to each other. We try to discuss ideas. We incorporate information. So we are open systems in every matter.
And why is it equal to constant?
It is equal to constant because it is a system. We have to make a boundary. We have action, we have organization, and we have a system. Now, if we have to define a system, we have to fix certain thing. So we have fixed that the system is equal to some abstract constant, which is equal to the action and organization.
How do you define action? Grootheid can be translated into English. De grootheid waarin je de actie en organisatie. How do you quantify action and organization so you can atom and...
Yeah. Action, as I told, action is the difference between the kinetic and the potential energies
Then I understand.
integrated over time. Organization we will eventually come to know.
Sorry.
Yeah.
So just a moment. So the constant is actually arbitrary.
It's a system. It's a system. Like,
do you need an observer in order to set a constant, or just?
we can define a system. Like, it depends upon the person who is investigating the system. Like, if I consider myself as a system, I am a constant entity. I am a constant entity. I am not random. I am a constant entity. I am made up of certain fixed parameters. Yeah?
For a certain time.
Yeah, for a certain time.
Yes.
So, yeah, this organization and action, they are temporal dependent. They depend upon time. So, what happens when system may get some quanta or something from the external surroundings? It will get excited. And again, it will try to reduce its energy state by again emitting the quanta. So that's what, the time dependent. We are always evolving with time.
Sorry.
Yeah.
But if I see it correct, but correct me if I'm wrong.
Yeah.
But you say it can, an action is quantified as energy.
Energy into time.
Yes, energy into time. So if I lose, and if a system loses energy, that means to get action plus organization constant, it will automatically increase organization.
Yeah. It will.
Always.
Yeah.
Okay.
If it reduces its energy, then it will become more organized. The interactions will reduce to some extent.
Okay.
Like you can say water. The liquid water, they are constantly, it is in the liquid state of motion. Because it is in liquid state of motion, why? Because the random motions of the molecules. But once I freeze the water, I take out the energy from that water molecules. I force those molecules to reach a lower energy state where they condense to become ice. I reduce the action, I increase the organization.
And what with systems that, for example, are very chaotic, you add a little energy, they have a reaction, and as a consequence of that, they become more organized. Like when you have this saddle points in. How does that work then with the? Because I can imagine systems that are chaotic, but with entering a little energy, reaction occurs, and then after that they can reach.
So reactions may cause certain internal organizations to increase.
Yeah,
certain part of the system. See, a complex system is made up of n number of many intricate parts. Mm-hmm. There could be possible that certain organization occurs locally. Mm-hmm. It is possible. Because of some chemical reactions, there has been formation of some closure or some formation of some little local organization at certain part. But it may be possible that there has been an equivalent or more than that disorganization at a different part. It is always possible.
No, that's not what I mean. I mean, if you see a system and you have like this energy of the system, then it is sometimes you have like this bump in the road. And you can imagine that the system is like there at the lowest energy.
Yeah.
And when you add a little extra energy, it goes over the top and reaches a level of lower energy.
Yeah.
So in that case, wouldn't that mean that by adding some energy, you get more organization?
Yeah.
Or then how does that work with the constant? You say like if you add energy, it gets more chaotic, and if you extract energy, it gets more organized. But you also have like systems that goes with this little, in the energy, this little hill, and when you add a little energy, they can actually, due to bifurcation, they can actually reach another state in which they are more organized. So I have little problem in seeing how.
We'll come to that. I got your question.
Okay.
We'll come to that. It is a consequence of second law of thermodynamics. We'll see that.
Okay.
So we again find certain analogies. Organization we can define as a structure plus functionality. In a system, it has a defined structure. it has some functions to perform. And organization plus action, as we said, it is constant. And same if we come to the domain of statistical thermodynamics, again we see information plus entropy is constant. Entropy from the statistical thermodynamics perspective is disorder. Information from the classical thermodynamics perspective is order. So we can see organization and action have this analogy in the thermodynamics as information and entropy. So this is what I was stressing, that emission of quanta will make a system less excited and it will make it more organized with time. One more thing I would like to clarify. I started with the talk that the self-organization is a natural spontaneous process. That means it is occurring within itself without any external influence. The idea that you spoke about, I'm talking about you, that energy is being given to the system. So there is some external influence. But my talk, which I am focusing, is based on this self-organization, how system naturally evolves with time, without any external influence. Because self-organization I am talking about is a natural process.
But you said it were open systems.
Yeah, it is an open system.
You have external.
Yeah.
Is that the same? The same? You have this external influence.
It is having external influence, but it is not directed, because self-organization doesn't need that anything has to be forced to make a system getting self-organized. It is a distributive phenomena of the individual entities that are making up the system. So one more thing, we need to quantify organization. So we did one way, that we found out one way, as that organization can be defined as the inverse of action. It is like we have action, and if a system is more excited, it is less organized. It is other way stating that a system which is more organized, it will have less action. But how? We need to understand. We need a different form of viewing the system altogether. We can't view the form as a linear way to define organization as well as action. What we have done is that we have viewed the system as a network. A system is made up of entities. So we have viewed that the entities form the nodes of the system, and the interactions that one entity makes with the other entity as the connections, as the links. So what happens when one node interacts with the other node? It is equivalent that one entity interacts with the other entity. What will happen then? Some energy in terms of quanta the system will lose out. Some energy, maybe one interaction, maybe it will force another interaction to take place. A chain reaction may occur. So what we have done is that we have defined organization, or alpha is the organization. It is equal to n, m, these are the constants, you can leave it. It is h. H is the Planck's constant. It is divided by the summation of the action of all the entities. It is like stating that the organization is the ratio of the quanta flux, that is the quanta that is being transferred from one interaction to the ratio of the total number of actions that are taking place in the system due to correlated action.
Can I ask you a question about this?
Yeah.
Do you mean that for the same process or same functionality,
yeah,
the action will be lower in an organized system? Is that what you say?
Yeah. Action will be lower in an organized system.
Yeah, for the same process. Or for the same
for the same process.
So that if you are not very learned,
yeah,
and you learn a task, then the task that you do will take less energy the more organized you
the system will become more efficient.
Okay.
The system will become more efficient. That is again self-organization. We are learning from the environment. It's a feedback loop. It's a feedback loop. Yeah.
Do you assume in this kind of method, you assume that the network is a fixed number of nodes and connections?
This is a very crucial question. Because at this point, what we see is that a system is made up of, it is open. First of all, the system is open. So it is natural to assume that it may incorporate nodes from the outside. That is one thing. But again, that becomes very tough. It becomes very difficult to analyze because it becomes non-deterministic. And what we are doing is that we are not focusing on the system. We are focusing on the process. We are focusing on the process, how the interaction is propagated through the entire system. How local organization evolves inside the system. So it is irrespective if nodes come outside the system, come from the surrounding and it enters into the system, it is irrespective. Because process will occur even the system is isolated or even the system is open. But the direction of the process will be different in both the cases.
Yes, it also derives from the previous definition that you gave, that the system is action plus organization, and it is constant. And in the same manner, this is problematic because it does not account for evolutionary processes. For example, I can give you just a funny example. You said, I'm a human, okay, it's a human organism, it's a system, but then I input some energy into it, like heat, and I become cooked. When I become cooked, I'm not a human anymore, I'm a dinner or something else.
No. If you incorporate
so
energy,
the constant there, something in the definition does not account for really structural differences that can happen while energy comes and goes. So this is already reflected in the previous definition and also here in...
No, actually, if I am a human being and if I get energy from the outside, I still am a human being. So what is the...
Till a certain extent, till a certain limit.
Yeah.
At a certain limit, this does not hold anymore. The very definition of the system changes. So, and the same thing happens when we observe any evolutionary kind of a process, whether it is destructive or creative. So, I would like to know how you account for this in your...
specific, maybe what you want to know specific.
How it for here, for example, in the last slide. Just a moment.
Is your question what happens if the system breaks down?
Yes.
Does it change?
Yes. It seems that there is. It seems from the definition you gave, it seems that there is some kind of a continuity which is unbreakable. But you did not mean this because every system can be destroyed.
So it depends upon what you define a system is, because initially the system can be a big entity, and once it breaks down, we can focus the individual parts as system again.
So the definition does not account for the boundary conditions of the system when it is created or destroyed. It is just when it exists.
Yeah.
Destroyed or when it becomes something other, something different.
So it is an instantaneous definition which we are speaking about.
Okay.
Because we can't generalize for an entire time that this will remain like this.
Yes, I just try to understand what is the model that
you
build.
Sure.
I also have a question. If you define organization as the inverse of action, like 1 over or a constant over, shouldn't you multiply then to make it constant? Because if you say if you add it mathematically it gets constant. But if you say it is the inverse, you should multiply it to make it constant, no?
It is irrespective. It is irrespective. If you add it, then also see. You can think it like this. When I talk about organization plus action, I talk about the structural definition.
Mm-hmm.
When I talk about the organization multiplied by action, I talk about the functional definition.
How can those two be different?
Organization, a system has both structural as well as functional properties. If I define a system in suppose in space,
Yes.
it will have certain spatial properties, it will have certain temporal properties, how it behaves with time.
Yes.
So if I talk that the system is action plus organization, that is equivalent to saying that the system is a summation of order and disorder. I defined action as disorder, organization as order.
Yeah, but later you define it as the inverse.
So I come into the functionality. System is composed of entities. It will interact with each other. It will give some energy outside. So it is a time-dependent process. I talk about the functionality that is occurring inside the system.
So you actually have two completely different definitions for organization.
No.
In one it is you add it with action and then it stays constant. So you have like if action is X, organization is minus X.
Yeah.
And in the other you say if action is X, organization is 1 over X.
Yeah. So what is the disparity between these two definitions? Means how you can say that both are not related?
I see just a mathematical problem. If you say action is X, then organization is either minus X or 1 over X. It cannot be both. If I try to quantify it in my head.
It is tough to quantify because organization itself is an abstract quantity. Organization itself is an abstract quantity. We have a quantification for action. We have an entire physics for action, but we have no physics for organization. Organization is still a very difficult term to express in form of physical equations. We don't have anything such. And we will gradually come to know that how action and organization are actually related as a law.
Atanu?
Yeah.
Could organization have something to do with topology instead of with functionality?
Topology means in this
form. Shape.
Yeah, that's what I told. Because if I speak about the action plus organization definition, I talk about the structure. That's the topology. But when I speak about the action multiplied by organization, I talk about the functionality. How the system behaves with time. Due to emission of quanta, due to growth of the internal nodes or whatever you can say. So this is the pictorial representation that you can say that due to the incoming nodes, or you can say that the trajectory of the system from one state to the other state, it evolves with time because of the emission of quanta continuously. This is the temporal definition. So this is a bit of mathematics that we have tried to do. As I said that the system is the constant and the system there, all these things are instantaneous, they depend upon time. So what we see here that the organization at suppose t plus 1 means one interval ahead of this instant is a function of the earlier instant of organization and action. Now one more thing, the action I have made the action as represented the action as Qt. Qt is nothing but it is the summation of all the actions in the system. It is a summation of all the action, individual pairs of action what I was speaking about. It is a summation of all those things. So here we come to a interesting part. If the organization at an earlier time was greater than the action, and if the organization was lesser than the action at an earlier time, how the system will behave and how the feedback loop will be occurring, because we are now entering the domain of self-organization as how the system communicates with the surroundings. The system has to communicate through some feedback loop. It has to check its state continuously with the external surroundings. So if the organization was greater at an earlier stage, so the system will prevent itself from getting further organized because it is already organized. But if the action was slightly higher than the organization at an earlier stage, then the system will try to organize further. It will try to organize further into a more stable state as compared to the surroundings. Finally, what we come to know is that if there are two time-dependent quantities and if one is increasing exponentially and another one is decreasing exponentially, then we can easily define a power law. So finally we end up getting a relation between organization and action as a power law expression. Now this has a very interesting outcome. Why this is interesting? We will see that shortly. Now we come into the domain of thermodynamics. This was all the mechanistic dimension of self-organization that I was speaking about. Now I spoke about the spontaneity of self-organization, and spontaneity incorporates the thermodynamic dimension to the self-organizing processes. Of the three laws of thermodynamics, the second law is of the prime importance for every process. What we see here is a pretty interesting picture. This is the structure of a system, and the structure of the system, a system tries to preserve its structure. A system never spontaneously evaporate into the surroundings, like it doesn't. The molecules that our body is made up of, they just don't fly away. There is certain boundary, there is certain barrier which protects us from getting disorganized completely. So this is the thing where thermodynamics comes into play. The second law comes into the play. The second law for isolated system is different. The second law for isolated system is that the system will gradually become disordered with time and it will completely vanish off. That we don't need. We need thermodynamics for the open systems. How these open systems behave with regarding to the thermodynamics and energy processes. So we see one example of activation energy. If two molecules are interacting with each other, there is always certain energy barrier that has to be crossed before any final end product is obtained. So this is a simple example, like the rock has to be transferred to the state B, which is of course the low energy, the low potential energy, and so it has to be transferred over a hill. It can't be a spontaneously occurring process. It has to have a certain external influence. So this is the activation energy or the boundary, the potential barriers. In nature there are potential barriers. These potential barriers prevent processes to simply occur. These processes, they fall between those potential barriers, those traps, and they can't get out from those. Yes, you have a question.
If you speak about boundaries, you're speaking about a boundary that prevents a system from going to one energy state to another, not a boundary that kind of surrounds the system.
Not the physical boundary. I am speaking about the energy boundaries, the potential barriers, the potential wells.
Yeah, okay. But isn't, sorry if I repeat myself, but isn't this one the state case that you can have actually entering action into a system and get more organization, so that action plus organization is not constant in this system? You have this system, it has like, you add action, so the action increases, and as a consequence of that also the
action
increases.
If the action increases, what will happen?
The stone will roll off the hill, I suppose.
Yeah, so the stone rolls off the hill and it reaches a minimum energy state. It becomes organized.
Yes, isn't that a problem? More action and more organization. And action plus organization is
but it is constantly dissipating towards the surrounding also. Now, one more thing. What is basically you are trying to imply? Because here our system is the entire thing, the rock as well as the uphill. This is our system.
The human pushing is
No,
coming
the
from
human
outside.
pushing the human is giving some action, the influence, the external influence.
Yes, that's
But the entire system is a combination of both. First, the problem everywhere it comes with our perspective as how we define the system.
I think my big problem is how do you define organization? Because a system is the organization plus the action, and the organization plus the action is constant. And I really have a problem to understand what is it you mean with organization. At one point you define it as the inverse, and you have a definition, and I can completely follow that. But the moment that you say action plus organization is constant, then, well, that's a different definition of organization. That means you define organization as...
See, you can imagine like that bottle. That bottle, it is a structure. It is a structure at an instant of time. It has certain action because of the molecules that it is made up of.
Yes.
And it has certain organization because it is stable.
But what is organization? How do you define organization?
Organization is
I think that's my
order.
problem.
Organization is order.
Yeah, but if you say I can add it to action and get the constant, you have to be able to quantify
Yeah, because
it.
this object is particularly it can be quantified in in spatial space. I can quantify that object in XYZ coordinates.
Yes, but how do you quantify the organization? That's order. And I have an intuitive idea of what you mean. Of course, organization is order, and I understand what you mean. But when I think that's a mathematician in me that says like, what is the definition that you can actually calculate it with, and then because what is order? We have an intuitive idea
Yeah.
what is order, but what is order in your?
That is the search where we all are working upon. What is order? We don't have a
So you don't
definition.
have a definition like.
We are trying to. We are
You're
trying to model.
find, okay,
We are trying to find out.
Okay.
This is a big problem because we don't have specific definitions. We don't have. Yeah.
You can, sorry, you can think of order in this situation we are talking about. For example, if you mean equal distance of each element, and you measure the distance from one element to the next one, and they have to be equally disposed.
Distributed.
So you can
Yeah.
put that on a
I'm completely agree with you, but at that moment you're giving me a definition of order. You're giving me I think I have a feeling like, okay, there are a lot of different ways to define it.
Yeah.
But if you're, as a civil engineer, you're trying to quantify and doing thermodynamics, you need to pick one definition and try to work from there. If you keep changing the definition halfway, wouldn't you get into
the
a
formula
more
of order will
consistent
depend
theory?
on the system and what you want to achieve.
Yeah. It is time dependent. See, there are two properties of organization. One is it is space dependent, and another one it is time dependent. We need to carry on with both the things.
You can have a scientific definition that has both time and space.
We don't have even a scientific definition for both spatial as well as time for action. We don't have. So we don't have even a definition for a specific definition for entropy, or we don't have definition for disorder. We don't have definition for information.
If you work with information and you read books about it, okay, a lot of the authors disagree about
Yeah.
what the definition is,
Yeah.
but every author at least gives, I follow this definition.
Yeah.
This is the definition I use. So I'm asking you, what is the definition you use?
Yeah.
And
I
feel
cleared that part. I spoke at the first self. That organization I view as it depends upon two parameters. One is the spatial parameter, another is the temporal parameter. Spatial parameter defines its topology, the structure that you were speaking about. The temporal parameter will depend upon its functionality, how the system evolves with time. So it gradually gives us two different ways of thinking the organization.
Can you give me then two definitions or also? Do you have then two definitions or?
No.
No.
The two definitions, they will seem like quite different from each other, but after all they are the same thing. We are trying to identify organization from one way and we are coming from the other way. That's it.
Now I have actually a question and a remark here, because we are arguing about the substance philosophy and process philosophy.
Yeah.
And they never come together because they both view it from a totally different angle.
Yeah.
You cannot compare them.
Yeah.
Left is left and right is right. So that's my argument to the... You
Can
will never get out of this, eh?
No, can you explain to me, because I don't know a lot about it, so I really want to...
Let me first make my question.
Yeah,
so,
please.
From what I heard from you,
yeah.
Organization seems to be like an action-free state, which
yeah.
results into order.
Yeah.
Right?
Yeah.
So it's equilibrium.
Yeah.
Right. Right. Finished. Right. That's process philosophy, and some philosophy in philosophy as beatitudo. That's a piece of rest, right? But how do you get that? You have a perpetual motion and perpetual influence from the outside, and your system is always the system you have defined in time and space. That's what you're saying.
Yeah. Yeah.
Okay, so thank you. But to explain that,
yes,
you have to become a philosopher. And there is one in front of you. He wrote a marvelous thesis on that, right?
Any further questions?
But you cannot, I mean, in my honest opinion, you cannot reconstruct from the basic mechanical approaches your system.
Yeah, yeah. We have to take some another approach.
Right. It's a different approach, right?
Yeah. That is the problem we are facing nowadays. We tend to work on the traditional methods more and more. We want to refine those areas, but we are not reaching anywhere. This is the thing that I was speaking, the potential barriers that nature has. The activation energy, it preserves the structure. It preserves the molecules, it preserves the structures of atoms, the electrons, whatever you say.
Activation energy preserves?
Activation energy preserves the structure.
Okay.
Structure. Entropy. Entropy is again a disputed concept in some sense, because some of the people view entropy as a disorder. Complete disorder is entropy. But other way of looking entropy is that if you have certain energy at some place, it has a natural tendency to move. It has a natural tendency to spread out. So what I feel that entropy is better defined in this perspective, that it is the natural tendency of energy to spread out instead of getting fixed somewhere else. It has a natural tendency. Now, if we use this definition of entropy, it reduces many of our problems in defining systems and problems in defining structures.
Excuse me, when entropy increases, does information decreases?
Yeah, that is a statistical thermodynamic sense. Because entropy, according to them, is disorder, and information is order. So that is again different. Open systems, we all are open systems. So we all are open systems, and we consume our free energy to perform work over the constraints. Free energy, any system is made up of two kinds of energy, the free energy and the bound energy. We can't utilize the bound energy. We use the free energy to perform work. So what do? We use the free energy to perform work on the constraints. We use our energy to modify the constraints at our will because we want to achieve something efficiently. And the open systems like a flowing river, our human body, or anything you can say, the plants, the trees, they are constantly growing. They have a tendency to grow, and they always have something flowing through them, and this flow it has a tendency to optimize that flow, optimize the channel through which everything goes on flowing.
Can I ask you from where the notion of free energy and bound energy come from?
It comes from the classical thermodynamics, the Gibbs free energy. Gibbs free energy, if you have heard of. The free energy is enthalpy. The bound energy is the temperature times the entropy. So every system, the Gibbs free energy is equivalent to the enthalpy and the summation of this bound energy.
In your concept here, free energy and bound energy must be a spectrum which moves continuously between the two. I mean, they move continuously.
No, bound energy is not moving. Through any system, there is always certain kind of flows up.
But it changes through free energy.
Yeah. It tries to modify. It tries to modify the flow. It tries to optimize the flow. We will come across to a different, altogether a different law, the constructor law. So what is my proposal is that we need a different form of mechanics. We need a different form of mechanics where we can incorporate the laws of thermodynamics as well as the Lagrangian principle or Hamiltonian principle or the principle of least action, whatever you say. We need to incorporate both these things and then we can come up with a more generalized law. Because thermodynamics is something like, you might have heard about the direction, the arrow of time, the direction the time follows. And classical mechanics is reversible. Thermodynamics is irreversible. So finally we again come up with this curve that we saw at the first few slides, that is a normal distribution curve. What I told during these first few slides was that the mean tries to converge towards the central area because of the central limit theorem, because the random variables, they are not correlated. They are independent of each other. So when we have independent random variables, they try to focus towards the mean. But what happens when we have dependent, correlated random variables? We come up with a power law, Pareto distribution, where you can see that the distribution falls off, like maybe a power of 1, 2, 3, anything. It depends upon the law. The 80-20 law. 80% of the work is done in 20% of the time. This is, I would say that the 80% of my presentation can be conveyed in 20% of the slides. It's equivalent. So we come up with one more this functionality, regarding the functionality of us defining a system. The system can be viewed as networks. The networks, like the agents, they are interacting, they are the nodes, and the interactions, they are the links. And this is defining an abstract notion of the system as a networked structure. And this will enable us to understand self-organization as a distributive phenomenon. So what one Professor Atanu he has done is that he has given a concept that every element, every nodes, like even we are interacting with someone, we are potential energy reservoirs. So every network is composed of nodes which are nothing but potential energy reservoirs. And these potential energy reservoirs are constantly interacting with each other. This is a very innovative concept that Professor Atanu has given, I would say, a breakthrough in networks research. And these nodes interact by emission of quanta. This is one of the figures from his slides. You can see that if I focus on a specific node, then also you can see that the nodes are also made up of number of entities. They are also again interacting with each other. One more thing is that networks are ubiquitous. Everywhere you can find networks. The transportation networks, the airline networks, the communication networks, the social networks, every areas They are networks. Economic networks, the internet. And this is one of the major discoveries that Babasi and his team gave regarding the 80-20 law, that the 80% of the network is made up of only 20% of the nodes. Those nodes are nothing but the hubs. We speak about hubs like the ECCO group. It is itself a hub. The whatever universe community is itself a hub. The university is a hub because there are many number of people coming with different backgrounds. They have different social neighbors. They have different social connections. So it is a hub. It's a common platform. Yeah.
What causes the node to emit quanta?
It's the energy transfer due to interaction.
How does that go?
If one node, see, what I told that the agents or the particles, which are combining the system, I am imagining those entities as nodes. So they will be in constant motion. According to the third law of thermodynamics, no object can reach a state of complete order even at 0 Kelvin. Means 0 Kelvin cannot be reached. Every object has certain minimum energy, a 0 point energy that we say. It will oscillate from its mean position. So once that oscillation starts and we have a collective entities, it will interact, and that interaction will cause the quanta to emit. Dissipation will occur. This dissipation may cause the quanta to eject outside the system all throughout and to the surroundings, or it may cause the quanta to reject towards the neighboring entities and start a chain reaction.
It's a bit that Francis is not here, but I think that's what he calls the challenge.
Yeah, challenge propagation. This is the law that Babasi and his team gave. That is a probability that one node is connecting to the another node behaves as a power law. This is again a consequence of two important things. One is the preferential attachment. Another one is that the networks are growing with time. They are dynamic. They are not static. For a network to be dynamic, those networks, or in this case, those systems should be open. For the preferential attachment, we have thermodynamics. Because if we have three ways to achieve some least energy state, and the nature will naturally select that particular trajectory to reach that lowest energy state in which the time consumption would be minimum. That is the mechanics that I was talking about, including thermodynamics and principle of least action. Least action principle incorporates least time or the shortest trajectory.
Is time and energy not synonymous here?
Yeah?
If time and energy are synonymous,
Time,
the least time,
yeah,
or the least energy is that?
No, energy defines the state. Energy defines the state. Time is continuous. Time is a parameter that will define how that process, how that state is reached. Time is our controlling parameter. We will check whether that time is the shortest or not. So this is what I was speaking about, the preferential attachment. Certain directions are naturally selected. Certain directions, certain processes, certain directions for evolution or whatever you can say, they are naturally selected. They have certain energy as the framework, that the second law of thermodynamics, you can say that certain trajectories in evolution are naturally selected. There is preferential attachment. So basically our entire thing boils down finally that how large scale networks self-organize. Because large scale networks means complex networks, generally speaking, and complex networks are, if I put the idea of complex networks into this thing, into my talk, then every system as a complex system can be viewed as a complex network. So how complex networks, large scale networks, how multiple networks, they are self-organizing with time. That is our main idea to study. And why power laws? Means what is the idea behind the ubiquitous nature of the power laws? If there is a thunderstorm or if there is a lightning, we see a pattern. We see, if we see the energy dissipation rate, we will find that the energy dissipation rate follows an exponential increment and exponential decrease. Maybe the patterns for the earthquakes through the rocks, the pressure developed, everything has a power law explanation. But why this power law is ubiquitous everywhere? We need to find a generalized law that will help us understand that why power laws are so important.
Can you give an example of network growth?
Excuse me, I didn't hear.
Can you give an example of network growth?
Network growth, internet, Facebook.
I would like to understand the mechanism better. So could you explain, give an example of the mechanism of network growth?
Yeah.
So
Have you heard about the 6 degrees of connection? Yeah, I haven't heard. It is a very amazing thing that you can be connected to the President of United States by less than 6 people. So you can understand.
Provided you find them.
Yeah?
Provided you find them.
Anyways, you will find him. Actually, I couldn't edit the slides. I had one very nice picture that I wanted to show, that how I got connected with Professor Francis Halligan. I come from India and it's a very small place compared to Europe, the place where I study. And basically I got connected with him during my undergraduate studies. And how I got connected? I got connected with Professor Francis Halligan with less than 4 degrees of connection. 2 completely disparate people. And even more interesting is that after 1 year, I could find even a lesser route, that is only single degree of connection, gave me a direct contact with Professor Francis Halligan. One of the guys is Clement. The second route that I was talking about is Professor Gerard. I knew him and he knows Francis directly.
That's because you have a common interest.
Yeah. And that was the hub. The LinkedIn gave us the hub.
So
This is the...
gross explanation.
We live in a small world. We live in a very small world. Everybody knows everyone else. I think your doubt is clear regarding network growth.
Well, I understood your slide as saying networks grow by means of naturally selected the directions that will be least energy intensive. So what you're talking about is just how networks are connected, or how nodes are connected in networks right now?
No, I am speaking about how the energy and the network growths, they are interrelated. We have a concept of networks and network science in a pretty mathematical terms in terms of graph theory. We have nodes, we have networks, and we directly connect them. We have algorithm to find the shortest path and all.
So
But
the network with nodes and interactions, then it would grow by means of the directions of the kind of organization that is least energy intensive.
Yeah.
And can you give an example for that? Like, I mean, theoretically it makes sense, but I can't picture it. So maybe internet could be an example, but can we...
Let me think. We have a river flowing. It has some flow energy, and there are a number of tributaries. So suppose I place a rock in one of those tributaries, so it will act as a constraint. So the river will try to force that rock, but it won't go that path. So naturally, it will try to find the least possible or shortest route, or maybe a path where the energy requirement for the flow would be lesser. So it will find an alternative path.
So there will be a new tributary.
There will be new tributary.
Because to overcome
Yeah.
this energy.
Yeah.
Energy
And that's how you can see
how the
network grows. This is a picture. One of my friends took it. It is a, you can see the idea that I was telling you. A leaf, it has veins. Through the veins, there is always a flow of the salts and water and the magnesium, chlorine, potassium, everything. And see, you can see the design we get from the veins. They are nothing but the channels for flow. This is what I am speaking about, the networks, the growth of networks and the preferential attachment, how the path is naturally selected, how the thing behaves with time. So this is actually the law that I am stating here, that is more known as the constructal law, that if a system, a finite size system, if it has a tendency to morph, it has a tendency to persist in time, then it will morph in such a way that it will give easier access to the currents that are flowing through it. We can say the growth of networks like our neural networks, the economic networks, the transportation networks, they all try to optimize the flows. They all try to optimize the flow and they try to generate a design at the global level. We can see self-organization even working here.
That means that the rich become rich and the poor become poorer. Also.
Yeah. Yeah, rich becomes richer and poor becomes poorer. That's preferential attachment. This is one of the examples that I got from the satellite image of my institute. The black circle is my institute. I have highlighted these two areas. One is the red one and another one is the blue one. Now you can see a pretty interesting thing. The red one, the area that is confined in the red box, that is more of an industrial estate. You find the IT parks, you find the commercial areas, you find the shopping malls, that area. This area is predominantly a residential area, the bigger box. You can see how a thin line, if you can visualize here, a channel has been provided, how initially the people settled with the nearer towards the commercial areas and how gradually the flow occurred towards a more focused area where you can see the pattern. If you magnify the image, you can see a exciting pattern. The fractals, you can see how the economies have developed, how the roads and how the houses they have been placed. So you can see the cities, the growth of the cities as a consequence of self-organization, as a consequence of flow, the transportation networks. So what is the aim? The aim is that, again the normal curve, what we see at the one end is the Newtonian paradigm where it is a simple causality physics, reductionism. Another end we find that is disordered complexity, that is entirely thermodynamics, statistical thermodynamics. We make laws but again we end up doing average, we end up doing the what would be the mean temperature. When we speak that we have a gas in certain container, we speak the mean temperature of the container. So that is that part. What we should really do is we should find out the laws behind the organized complexity. That forms the majority, which we need to do. And how can we do that? Defining a new form of mechanics that I told you first, through thermodynamics, through mechanics, that is one possibility. But for that, again, the system in nature, they are non-deterministic. Principle of least action is completely deterministic mechanics. We need certain rules, certain laws, maybe that could be probabilistic. Even a guy has developed a stochastic least action principle. That is one more breakthrough, I would say. And Professor Arto Anila is working in probabilistic mechanics of thermodynamics as well as principle of least action. So there are still quite many avenues where we can work. That's it. Thank you. Anyone has further questions? Comments, criticism? This is my first seminar.
So, question, but I have a question with your single causality and disorder.
Yeah, yeah.
That's continuum there, right?
Yeah.
Are you sure that this is continuum?
No. I show the graph. That is a normal graph where the nature is made up of organized complexity. But we are either studying the disorganized complexity that forms one extreme, or we are finding like reductionism approach towards another extremity. We need to focus at that center. We need to find laws because there's where self-organization is taking place.
And what is your middle section of the Gaussian curve different from system theory?
No.
No different. Is the principle.
Yeah. That is the thing we need to identify. We need to form laws.
I'm trying to find my question because you're discussing self-organization systems.
Yeah.
But in what do you have in practice in mind of those systems? In practice, what do you have something in mind that you say I want to organize this or study this in practice, or is it everything? Or do you say you discussed internet? But is it everything, or is it something specific that you want to study, or what is that?
Basically, I start to focus with the networks, like the internet, and then I would like to generalize the laws of networks to study local interactions and how systems in general can be imagined as networks of interacting agents.
Yeah, because you see, I have read some books about self-organizing systems, and for example, they take a much more physical approach.
Yeah.
For example, the people discuss, for example, affluences. An affluence is also a self-organizing system. Not that I agree with that, but that they use it as a physical system, which all of a sudden changes from one condition to another one. But in internet, as a system, it's something completely different. So how can you combine those self-organization approach to both? I think that's terribly difficult.
Yeah, that's difficult. Because
that's why I'm saying, what are you studying in reality? You say networks, but you also have the affluence, you also have all the people in front of me were discussing self-organizing systems, which is something completely different, more or less. So it's a very broad area.
We are trying to find out the generalized law.
Yeah, but it's a generalized law.
Do you have a plan of attack? How will you get to there? How do you? Well, when we think you start from one system, you see I have a different system that reacts different. I would try to see if I can integrate those, and then we have already a law that's a little bit more generalized. To go like that,
step by step, we need to refine. We need to refine.
Do you have an idea what the first steps will be at this point?
First, we need to find out, because networks are ubiquitous, that I have been stressing.
Yes.
So we need to find out how self-organization is occurring in networks. The laws, networks behave as power laws.
Yes.
So power laws are again some powerful implications of nature. We need to identify why we have certain form of scientific research going on where we get the statistical data and we try to program it, we try to do some regression analysis and we fit it and we get a power law. But we don't give an explanation.
I have a problem with the word that you call internet a self-organizing system. That's the problem I have, because it's in a certain way internet is not a physical system.
No,
of course it is, but it is not in a certain chemical type of system. It's a very it is a system which is very structured in a certain way. Not what I mean the users. The users can do everything. they can, I don't know what they can do, but the system itself is very strictly organized using strict rules of communication. And you understand that? So it's not in that sense a self-organizing system.
Yeah.
Or,
Would you allow me to
Yeah, yeah.
to this?
Yeah.
You mentioned Adriaan Billon, at least Atanu.
Yeah.
And one of the recent books of him, which is about the constructor law and how you apply it in life around you, actually gives the example of the internet and analyzes many aspects of the internet as fitting into the constructor law. And he says that the internet is nothing more than a transport system for information, a transport system for information, and that we shape the internet according to the best or the optimum transport of that information. And that is again the constructor law.
And internet is also centralized in some way by the DNS system, for example. There is central servers which has a special effect on the network, on the contrary of biological system, where there is no center at all.
We need to.
In internet, we have some kind of centers.
No,
For instance, Facebook is typically centralized.
No, Facebook is a hub.
Yes,
Facebook is a hub.
It's not like a biological system, a decentralized system.
Yeah, but no, you have some central parts. If your brain is totally destroyed, you die. If your heart is destroyed, you die. So you have some organs, some parts of the system which are essential for its functioning.
Yeah.
I don't know, but for me it can also depend on how do you define Facebook. If you say like every person on Facebook is a node and has links to other persons, then if you start to examine that structure, you can see like laws emerge that are completely independent of the fact that, well, all the data is stored on a server somewhere in America. I don't know where it is stored. But that's, I think you have different, if you say Facebook, then you can look at it as, that's for me why I stress, like, what's your definition? What are you looking at? So I think that's a way to look at Facebook without actually having anything centralized.
I think it would behave in a different way, like not like it is now. If the physical network was without any center, I think the behavior of all the nodes that we are would be different.
But if we fix a physical network, then we restrict our options.
Sorry?
The network won't grow. The network won't be any dynamic in nature. It will be static.
I'm not sure. The P2P network, for instance, have some dynamic.
If we talk about the transportation networks, they are, if we fix the roads and if we focus on that area, then the transportation network is not a complex network because it is not growing. It won't follow any power law or it won't have any self-organizing properties.
There are two levels.
There is one point of critique about it's the name of the seminar is the physical foundations of self-organization or something like this. And if we look at it from a conceptual point of view, more philosophical point of view, I'm not sure that self-organization is strictly physical. We start from, at least in the ECCO paradigm, we start from system theory and cybernetics, which is a formation of certain formal principles or rules that can be applied to very different phenomena, physical, in the internet, in the best example that you give is the metaphor of network. A network is not a physical thing; it's a metaphor that can be imposed on many systems. So if we investigate mathematically, conceptually, what is happening in networks, we gain immediately insight into everything that can be mapped into this kind of metaphor.
Right.
So, in a sense, if you want to look to use the knowledge of mechanics, thermodynamics, etc., as a kind of microscope into a certain abstract problem, this might prove itself to be productive. But I don't think that the things you're interested in have strictly physical foundations in the sense of physics having to do with space-time, energy, mass, the fundamental forces and the interactions. These are already more specific examples of abstract principles. So maybe you can just do without physics at all.
But that was also my question, because you have what I call the avalanches. I don't know the name of the person, but you have Ilya Prigogine.
Yeah.
And he is the founding father, let me call him, of all of this.
Yeah, non-equilibrium thermodynamics.
Yes, but what he discusses is almost all physics.
Yeah.
It's all physics, and I don't think he discusses about networks at all.
No.
So that's what I'm saying. The terminology is correct, but when you say I'm going to study networks, you take a very small part of all of this, and even in my opinion, maybe I'm wrong, in self-organizing systems there is no. You don't can use words like entropy, okay? They are a little bit strange in that area. When you study a network, like internet, then that concept is not there. It's really in the physical part. Or maybe you say I don't agree, but that's mine.
I would really like to add a question to this, to the fundamentals actually of your talk. What are your assumptions? Do you list your assumptions somewhere? Because sometime you were mentioning something like every node is always in competition with another node. I wouldn't necessarily agree. I would already say that there you're taking out some clearly cooperative networks you're excluding from your observation because you're assuming competitiveness or also constant growth. It's not. There are examples in nature where there's degrowth. So I found your talk very insightful, and this ambition to find a theory that covers everything and that reunites also the social sciences and the natural sciences. However, I see the risk or the danger that you have assumptions that I don't know if they're very explicit, and they might exclude again some things, so that it's not a risk. Well, that's I did get some.
I started my entire thing based on two fundamental laws. That's the principle of least action and second law of thermodynamics. So both the things can't be challenged in any of the sciences. So
I think I do agree with her when she says like you have so many ideas that maybe at that point. Because you have so many ideas, you don't really look very well into one idea, and you can at some point indeed lose feeling with what it is exactly you're saying. I have the feeling like you use terms like organization, and I know I came back to that a lot. That I have the feeling you have a general concept, but there are so many different theories that go parallel, and if you start to use a concept from one theory and a concept from another, and you start mixing them, and you don't really know what are indeed the basic assumptions, the definitions, then you may at some point just...
That is the thing. We have different parallel ways, but we don't have a single connecting link between the different approaches. I'm trying to find that connecting link using principle of least action and second law of thermodynamics. Because no science cannot go against these two laws. So there has to be certain kind of link between connecting these parallel paths. Maybe constructor theory you are speaking, maybe the fractals you are speaking, maybe the network science you are speaking, maybe the systems biology you are speaking. There has to be something connecting.
Can I just make an observation to some question, because I answered that a little bit randomly. The internet, to make a slightly comparison to what you're asking, internet is nothing else but a set of procedures, TCP/IP. Right?
Yeah.
Nothing else but that. But below the lowest level is the whole physical nature, physics, and the applications above is all what we're doing here. So these two linking together, TCP had no idea what's going on at the upper level. Yes. They try to define a number of applications, and you can easily classify 5.6, and in 5.6 everything goes together, and then above this 5.6 you have an infinite explosion of repetitions of these applications. Now, if you take the end level application there and you try to put it together into the TCP/IP, he who knows TCP/IP says, of course, it's evident, it's clear, right? If you ask the physical implications of the lowest level, the physics will say, of course, that's evident. But the physics man, we have no idea what's going on at the first level. No idea. But indeed, if you talk him through it, he will understand, because he has the same level of intelligence as most of the people who are here. But there's no way of doing the stepwise. I mean, I heard a presentation yesterday of Professor Van Bendingen, the head of philosophy here, right? And he said, imagine, he says, that you ask me, how do I get from here to the station? And he starts telling me, well, you do one step, and then you do this, and you tell me all the steps. You will give him 1,000,000 steps to get there, and you will never find the station. That's exactly true here. I mean, he has a conceptual, high-level, beautiful model. You can have infinite aspects of that, and to try to pick out a example of that, it's nothing to do with his model anymore.
No, I do agree with you, but I think the difference for me is indeed you have all these theories, and you want to make a theory of life, the universe, and everything. And
that's not a theory, huh?
No, but try to find the laws behind that.
Yeah.
And I really think that's, I think, the most interesting thing you can do in complexity. I just think you need a path, a way of attacking the problem, and
then generalizing and trying to generalize through different areas, that how I can link different parts.
So I really think that making such finding those laws is very, very interesting, but I think you also need an angle to start, nibbling at the problem. If you try to nibble from all the angles, will you get anywhere? That's what I
understand. I think what he is
what
he is saying is that self-organization has a physical basis, but self-organization is not the physical basis. Right? So, we can't talk about those together. We have to talk about the physical basis. We're talking about the self-organization. You have two different things. Dissipative structures, you can beautifully apply that to his theory here. Beautifully applied, but not in the context of pre-regime, in an extrapolated aspect of the end order.
Yeah, directly you can't plug up these things.
No, you cannot, but you can indeed.
But there will be a certain link between from this point to that point.
Maybe 6, I don't know.
that is the beauty of physics.
Right. And for he who sees through everything, which is Francis omniscience, there is no link. There's only science. It's omniscientific. What do we call it?
Omniscience. Omniscience.
Omniscience. Right. So he has 5 or 6 omniscience, omnipotence, omnibenevolence, and all these things. Put them all together, you have the perfect man.
Yeah, thank you.